All right. So we've got today's Tuesday. Test is on Thursday. I'll go over some of the mechanics of that in a little bit. And so today is sort of like the last day of new content for the test. Now, the nice thing is all of this content is stuff that you would have seen in the basic class, and nothing is really earth-shattering here. Nothing is all that new. We're just going a little faster and a little more in depth than you would have done in the basic class. Now, before I go into the PowerPoint, just let me ask really quick. I know I've got one question to deal with after class, but does anyone else have any questions over anything that's sort of coming up? There's only about 9 of us in the class so far, so go ahead and unmute yourself if you have any questions. Okay. If you do, chat's a good place to bring those up, and if not, that's fine. We can always connect later. I will start sharing the screen. There we go. This one. The PowerPoint is currently posted, so you can go to my courses and you can get a look at it yourself there. Okay. And I'm going to take this. All right. So today, a little bit of class business, so I can go over some mechanics that go on with exam 1, and then we'll go into the topics of the day, which include mass balance, which is stoichiometry, and balancing chemical reactions. Very standard for a course like ours. And then I've got 4 different examples, 5 actually, of stoichiometry that are in there. Sorry? There really are innumerable ways that a question in stoichiometry could be asked. So there's no way for us to cover every possible one. It comes down to a matter of reading, knowing what you're given, and understanding how to get to what you're asked for. And that's the process I intend to walk you through today. So with the class business stuff, the homework 3 has been assigned is due Sunday. Extra credit 3 is assigned is due Friday. Both of those, I dialed it back a little bit in terms of like the how tough things are on some of those homework so that you have time to study them for the exam. But these would be very helpful for you in studying for the exams. I encourage you to do these homeworks soon, before the exam, or at least give your best shot before the exam. The exam itself will open on Thursday. It goes from 12:01 a.m. to 11:59 p.m. So that's the window in which you have to take the exam. As a result of that, I won't be, and I emailed you guys about this, I won't be holding a class per se on Thursday. I'm going to leave you all Thursday for you to take your exam. I will, however, from 2 o'clock to 3 o'clock, reserve the time for office hours. So I will be here in this Zoom meeting, and if you have any questions or anything you want to ask about, stop on in and do that. So I'll be open and available, and you can just click on the link in the calendar and you'll be connected to me immediately. Okay? So those are the main things there. Now with the mechanics on exam 1, there are going to be 2 sections. And the reason there are 2 sections is because they're graded differently. And I can't have 2 different ways of grading in one section. So split up into 2. There's a multiple choice section. And for the multiple choice section, there'll be 8 to 10 questions at the time of the exam, and you get 1 opportunity to answer each one of those questions. So once, if you click, let's say C as the answer, the computer will say thank you and you move on. So it won't tell you if you're right or not. For numerical answers, which is the other section, again, about 8 to 10 questions there. You'll have put some kind of input in that's either like written, like you had to describe something before, an example. That would be like, describe an example of a solid heterogeneous substance. You'll get up to 2 opportunities to answer. So if you put in an answer like, let's say 14, and the computer says that's incorrect, try again, you will get an opportunity to try again. There'll be a small penalty, and you can submit, and hopefully on the second go, you get a correct answer. So that is why those are split up into 2 sections. That section is also timed, and Depending on how many questions are actually in that section, I can tell you how much time there is going to be, and I plan to have that done tomorrow. It's going to cover chapters 1 through 4 intro. And really going from the homework, quizzes, and lecture content, that's a really good example of the sort of things that are emphasized in chapters 1 through 4. I produced a study sheet for you. It's in chapter 3 content. And the exam 1 prep and mastering is probably one of the better things you can use to prepare yourself for this test, because it's going to be done via mastering. And so practicing in the environment is one of the best things that you can do for yourself. That said, I'll pause here. If you have any questions, ask it in the chat or unmute yourself and go ahead and ask. So do you guys, are there any questions over any of this class business stuff? Yeah, if there's no questions, then I'll proceed with balancing chemical equations. So this is the one thing that people seem to remember from any chemistry class they'd ever taken ever in their lives. You tell them you're taking chemistry, they're like, oh yeah, I could balance equations. So this is what people remember. So here's a common chemical reaction. Reactions are always written sort of like this. We've got on the left-hand side of this, that the tail of an arrow is facing. These are our reactants. These are things that we're putting together. Okay, so they're usually separate. They're going to bring them together. And then this arrow reads as yield. And then the right-hand side of the arrow is our products. And so reactants yield products. So these are the things that come together, something happens, and these are the things that come. Okay? So just realizing that these are reactants, these are products, that's a rather important thing. But mass balance is required, which means that if I have a certain number of atoms on the left-hand side, I have to have the same number of atoms on the right-hand side. I don't destroy atoms in this process. And not only that, I can't have an atom of carbon on this side and let's say cobalt on this side. That can't be. I can't have one atom change into another atom. It's a nuclear reaction. Those do occur. They're out of scope for this chapter. So the same kind of atoms need to be on both sides, and the same number of atoms need to be on both sides. So we're going to work through a couple of examples that will show you this. So here's one example. I've got, well, you should be able to name this. This is cobalt-3 oxide and solid carbon going to solid cobalt and CO2, carbon dioxide. It's unbalanced. Okay. So we want to balance this. Looking at something that's unbalanced causes me a little bit of physical illness. Where do we start? Well, I've got the same number of carbons on both sides. Whatever number is in front here is going to have to be in front here. I've got 2 cobalts on this side and 1 on this side. And I've got 3 oxygens on this side and 2 on that side. And that's something that is very intriguing to me, because maybe that's the place where I should start. I've got an odd number of something on one side and an even number on the other side. So if I put a 2 in front of this, seems like a weird place to start, but what I'm doing is I'm creating an even number of oxygens. Now I've got 6 oxygens. It's pretty easy for me to make an even number of 6 oxygens when I've got 2 on this side. So when I put a 3 in front of that here, I've got 6 oxygens on this side. 6 oxygens on this side, that works. I've got 2 cobalts. 2 times this entire thing means I've got 2 multiplied by everything that comes after it. So I've got 4 cobalts on this side and 1 over here. 3 carbons on this side and 1 over here. So I can put a 4 in front of the cobalt and then a 3 in front of the carbon, and now I'm balanced. And these things that we put in front of them, they're called coefficients. And what they tell us is the number of moles or molecules that are there. We don't get to put new subscripts in anywhere. That changes what the molecule is. So that's a definite no-no. But the number of molecules that are going on in a ratio for this sort of reaction, that we can change. Those are the coefficients. So that's an important thing for us to remember. Some of these will just be easier to balance than others. Thank goodness pencils have erasers, right? There's no real good strategy that I subscribe to. I just go with trying. Here's another example. This one is a combustion reaction. So I've got C4H10 plus oxygen goes to CO2 and water. This is not balanced. So again, just taking a quick look 30,000 foot view, I've got 4 carbons here, 1 on this side. I've got 10 hydrogens here, 2 on this side. I've got 2 oxygens here, and a total of 3 on this side. So again, I've got this odd even thing, but I'm not sure what to do about it. So I'll start with the carbon and hydrogen. 4 carbons on this side. I'll put a 4 in front here so that balances it. And then 10 hydrogens, I've got 2 over here, so if I put a 5 in front of there, I'll balance that. But one of the things that I immediately notice is I've got 2 oxygens on this side. 4 times 2 is 8, 5 times 1 is 5. So 8 and 5 is 13. 2 oxygens somehow becoming 13 oxygens is a when you are balancing, how much do states matter? Quick question from Danny. When we're balancing, how much do states matter? States don't matter at all. Not in what we're doing now. They will matter for something else later. But they're there just for information. All right, so again, I've got 13 oxygens on this side, and only 2 on this side, and trying to make a odd and an even thing balance is a little bit tricky. So I'm going to put in 13 halves. 13 over 2 times 2 is 13. This is balanced. Technically, there's nothing wrong with this. We don't like that phrase technically. Technically, there's nothing wrong with this. However, we tend not to have fractional coefficients in our balanced chemical reactions. You will see them from time to time, especially in the second semester, but we tend not to have fractional coefficients. Something illegal about it, we just tend not to do it. So I want to get rid of this half here. And the only way for me to do that is to go through and multiply everything by 2. So if I kind of bracket this and put a 2 in front, then when I go through and multiply everything by 2, that will get rid of this half. So 2 butanes times 13 O2s times 8 CO2s and 10 H2Os, that is my balanced chemical reaction. Okay? You guys should expect to be able to balance chemical reactions. The only kind of chemical reactions we do not balance in this class are redox reactions. There's a very good reason for that. It's a second semester topic, so you don't need to worry about balancing redox reactions, but you won't even know what kind of reactions there are. One thing that this book does, and actually general chemistry has done for a while, is they've sort of shied away from descriptive chemistry. So when you're balancing these things, you don't necessarily gain an appreciation of what kind of reaction is going on, what reactions are measured. You can't really change that for the curriculum of the book, but that's one of those things that's changed since I've started teaching. Okay, so now we got a balanced chemical reaction. Now that they're balanced, can we do stuff with them? Well, we can do something called mass balance, which is stoichiometry. And what mass balance allows me to do is determine the number of things that are going into and coming out of the reaction. So if I know how much of one thing goes in, like methane, I can figure out how much carbon dioxide comes out. And if you think about this, this is something that you're probably familiar with in terms of like cooking or anything else where you prepare stuff based on some kind of raw material or ingredients. So if I have so many, I don't know, hot dogs, then I know I can make so many meals for people who are coming over. So that's just a common thing. But with stoichiometry and chemistry, we do involve a little bit of math. So one way to look at this is that 1 molecule of methane, CH4, reacts with 2 molecules of O2 to make 1 molecule of CO2 and 2 molecules of H2O. That is a totally accurate way to read this. However, we rarely look at these things on a per molecule basis. We tend to view reactions like they're kind of big, right? So instead of 1 molecule, we might have 2. Instead of 2, it might be 4. And instead of 4, it might be like Avogadro's number of molecules, a huge number of molecules. So if that's the case, then we can say that 1 mole of CH4 reacts with 2 moles of O2 to make 1 mole of CO2 and 2 moles of water. So we know all these quantities in terms of moles, right? But usually we don't have balances. Like if I actually want to go and make so many moles of CO2, I don't have a balance that measures things out in moles. I have a balance that measures things out in grams. But when I read this chemical reaction, I cannot say, so this is not 1 gram of CH4 plus 2 grams of O2 makes 1 gram of CO2 and 2 grams of water. That is simply not the case. And that's because both of these things up here, molecules and moles, are numbers of particles, numbers of molecules. They are not gram masses. And so a gram of CH4 is not the right number of particles to react with 2 grams of oxygen at any level of completion. So a conversion needs to be done in something like that. So generally, the steps in stoichiometry, we tend to start, especially in this chapter, it will change in future chapters, but in this chapter, we tend to start with some mass of something. Figure out how many moles that is. We use a ratio, a mole-to-mole ratio, to figure out how many moles that we want to turn into, and then get the mass of that. So it's a 3-step process, 1, 2, 3 steps. So the first step in any of this is to first panic. You have no idea how to do something like this. Time to start reevaluating life choices. Then we cry, and then after a good cry, we convert to moles. Panic, cry, and convert to moles. That'll get you through anything you have to do in chemistry. And once things are converted to moles, we do a mole-to-mole ratio. So right here at this arrow, where we convert moles of A into moles of B, that comes from our balanced chemical equation. And then we go from moles to a final unit, at least in this chapter, that is typically grams. It doesn't have to be, but it can be. And in other chapters, it'll be volume or pressures or something like that. Right now, we're usually going to use grams. So here's an example. C8H18, that's octane. That's stuff you put in your car to make it go. If you have a Tesla, you're using coal. So octane plus oxygen goes to make carbon dioxide and water. And a little bit of octane makes a whole lot of CO2. So what mass of CO2 is made when a huge amount of octane is combusted? So 4 times 10 to the 15th grams of this stuff, that's an enormous amount, is combusted. Well, we can figure it out. Here's our general plan. I start with grams of this. I'm going to convert it to moles. And the way we do that is through a formula mass. We get that off the periodic table. I know the mass of 8 carbons and 18 hydrogens. I can get the periodic table, add them up, and we're good. And that comes out to 114.22. And then I can figure out how many moles of this turn into moles of that. So for every 2 moles of C8H18 that go into my reaction, which is this stuff, 16 moles of CO2, this stuff, is what comes out. And the 2 and the 16 come from my balanced equation, 2 and 16. So now I have units of moles of CO2, which I want to convert back into grams of CO2. So every mole of CO2 is 44 grams. That's where I'm at. So when I go through and actually do that, I do that math, I come out to 1.2 times 10 to the 16 grams of CO2. You want to convince yourself of that maybe later when you're studying. Go through and do this math, make sure you can do it. Part of the trick is also making sure you're entering it into your calculator correctly. Okay, so let me take a quick pause there and stop the share for a second and ask if anyone has any questions over anything they've seen so far.
I have one question. When we're doing the through the mastering, yeah, and you want us to put, for example, the question asking to balance the full equation, but you also want us to write the phases. You know how we have the little buttons that say XB, XA on the top? Do we put the XB whenever we're trying to put the phase as a solid, gas, liquid? Is that what we use for it?
Yep.
Okay, just making sure so I don't get it wrong.
Yeah. That's a great question. Glad you asked. Those are subscripts.
Okay. Thank you.
Great. Any other questions on this stuff? Okay, I've got 3 worked examples, and they are in terms of complexity, they get a little more complex as we move on, and they introduce some other ideas as well. So let me go back to sharing my screen. Okay. So here is the next worked example. So I've got this reaction, NO2 plus O2 plus H2O goes to make HNO3. This is one way that nitric acid can be made. So what mass of nitric acid, HNO3, can be made from 16 kilograms of NO2? That's one question. The second question is what mass of O2 will be needed? Okay. A couple things to notice about this. One is you take a look at that reaction right there, and you see you've got the same elements on both sides, but not the same number of elements on both sides. So generally speaking, you won't be told if a reaction is balanced or not balanced. If you see no coefficients in front of these, reasonably good chance that this is not balanced. So you should be able to look at on inspection and see if this is a balanced term. So we'll go through and rebalance this, and 4 NO2 plus O2 and 2 waters goes to make 4 HNO3. You can go through the balancing process on your own later, but that's what it comes out to. So now that we know that it's balanced, we kind of need an attack plan. So 16 kilograms of NO2, I need to get to moles of that. I don't have a kilogram to mole conversion, but I do have a gram to mole conversion. So I'm going to convert kilograms of NO2 to grams of NO2. That'll be turned into moles of NO2. I'll do my mole to mole ratio to get moles of HNO3, and then I'll be able to turn moles of HNO3 into grams of HNO3. A little sloppily written, you get the idea. So it is a really good idea for you to maybe lay out those steps. Something that seems really hard at first is really just a series of small steps that you do know how to do. So we're going to start with converting this kilograms to grams. So 16 kilograms of this stuff, every kilogram is 10 to the third grams. And then 1 mole of this stuff, NO2, weighs 46.01 grams. That's the mass of 1 nitrogen and 2 oxygens, 14 and 32. Next, 4 moles of NO2 go to make 4 moles of HNO3. So I've got a 4 here, a 4 here. That's why I've got a 4 on top and bottom. 1 mole of HNO3 weighs 63.01 grams. Okay. So everything cancels, and I'm left with 21911.8 grams. That's what my calculator tells me. That is way too many significant figures. I'm allowed 2. This is how I write the number with 2 significant figures. I basically round up. 21,911 is very close to 22,000. And to express it in units of kilograms, which the question is not clear on, just says mass. So kilograms or grams is fine. But can bring this to kilograms, the same as dividing by 1,000, that becomes 22 kilograms. Okay. So that's one simple way for doing it. Now the question's already balanced, but the next question is what mass of O2 is going to be needed? So again, here's the thought process. I'm going to go from kilograms of NO2, grams of NO2 to moles of NO2. Same first 3 steps I did before. But I'm going to turn into moles of O2 and grams of O2. That's the different bit. So just these last 2 steps change. And because those first 3 steps are the same, I can get here pretty quickly. 16 kilograms of this stuff goes to 1,000 grams of nitrogen of NO2 for every kilogram. Every mole weighs this much. But now, 1 mole of O2, that's my coefficient here of 1, there's nothing there, comes from reacts with 4 moles of NO2. Notice that these are on the same side of the reaction. That's fine. If I know the moles or grams of any one thing, I can figure out moles or grams of any other thing. It does not matter what side of the reaction it's on. 1 mole of O2 weighs 32.0 grams. So when all the things cancel, 2,800 grams is what I get to 2 significant figures, which is the same as 2.8 kilograms. Okay. So really, this is just 2 stoichiometry problems where I know the mass of one thing, and I try to get the mass of something else. I very easily could have started this process down here with 22 kilograms of nitric acid. I would have got the same answer. However, it's always your safest bet to stick with what you're given in a problem, just in case you made a mistake getting this number. Any mistake made getting this number and then carrying it forward would, may not work out in your favor. So whenever you get an opportunity, make a choice between using a given number and when you calculate it, using the given number is usually a little safer. All right, any questions on this one? Okay, if there are no questions, we're going to move on to the next one. What is the theoretical yield of ammonia in kilograms that can be made from 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen? It's weird. Well, first reason it's weird is because I have this new word, theoretical yield. What is that? Well, with any recipe or anything you're making, if you have enough material to make so many of something, you usually make a little bit more or a little bit less of it than what you expected. So the theoretical yield is what the math tells me I should end up with. So if I react 5.22 kilograms of H2, I should be able to calculate how much ammonia that gives me. Or if I was to react 31.5 kilograms of nitrogen, I should be able to calculate how much ammonia that gives me. That is my theoretical yield. There's something else going on here. In this particular reaction, I have this mass and I've got this mass. I've got 5.22 kilograms of hydrogen and 31.5 kilograms of nitrogen. Which one do I use? I don't know. One of these is going to limit the amount of this that I can make. So I'm going to end up using both. Does not matter which one I start with. But I start with the one that was given to me first. 5.22 kilograms of hydrogen. So here's my game plan. Kilograms of hydrogen I want to turn into grams. Turn that into moles. Turn that into moles of NH3. Turn that into grams of NH3. And then turn that into kilograms of NH3. Not bad. So here's me turning it into grams and moles. Forgive the fuzziness on that one. Mole to mole ratio. Moles to grams. Grams to kilograms. Okay, so I just follow my little game plan here. And when I go through and cancel stuff out, units cancel, but also I've got a 10 to the third on top and a 10 to the third on bottom. So I'm canceling away from kilograms in the beginning and then back to kilograms in the end. So I can actually make my math a little bit easier. Instead of just canceling units, I can also cancel numbers. And I come down to 29.4 kilograms. So if 5.22 kilograms of hydrogen reacted completely, I would make 29.4 kilograms of ammonia. Let's do it with the other one, nitrogen. So the only thing that changes in this one is I'm going to go from kilograms of nitrogen to grams of nitrogen, grams of nitrogen to moles of nitrogen, and then that will go to moles of NH3, grams of NH3, kilograms of NH3. So really, from here, these two parts and these two parts, that's not going to change. All of this is going to stay the same. It's just this little bit up front is going to change. So here's the bit that changes. 31.5 kilograms of nitrogen. Kilogram weighs 10 to the 3 grams. A mole of nitrogen weighs 28.02, and a mole of nitrogen, 1 mole of it reacts to form 2 moles of NH3. Okay. Good. And then I can figure out from the end here, a mole of NH3 weighs 17.04, and 10 to the 3 grams is the same as a kilogram. So just, you might notice that like all of this part up here is the same as it is down here. All of this stuff up here is a little different from what was up here. If I go through and calculate this, I get 38.3 kilograms. So if all my hydrogen reacts, I make 29.4. If all of my nitrogen reacts, I make 38.3. It seems that if I was going to make this much ammonia, I would need more hydrogen. So this reactant is going to run out first, making hydrogen what's called my limiting reagent. There are really good analogies that go with this. Your book uses a pizza analogy. People use hot dog analogies. 8 hot dogs, 10 buns. That most of you make 8 hot dogs with all the buns that you have, and you have 2 left over. But so my theoretical yield will end up being the smaller of these 2 numbers. So whichever these 2 numbers I get, the smaller of those 2, that is my theoretical yield. And that is the most of this stuff that I can make. So that answers my question. What is the theoretical yield there? that one. H2 is my limiting reagent. It runs out first. N2 is left in excess. So this answers the question that was asked. I'm going to ask a follow-up question. And I did a video for the class that does this exact same thing, asks the follow-up question, which is, what mass of N2 remains? So I know how much N2 I start with, which is 31.5 kilograms. It's my excess reagent. So how much of it is left over? Can I figure that part out? I can. It is not the difference between these two numbers, 38.3 minus 31.5. Because this is kilograms of ammonia, that's kilograms of nitrogen. We're not subtracting two different things here. That's not the way to do it. The way to do it is to realize what I'm asking myself is really how much nitrogen gets used in this process. If this is my limiting reagent, hydrogen, and it runs out, then how much nitrogen is needed to react with it? So if I know kilograms of hydrogen, I can turn it into grams, grams to moles, moles of hydrogen to moles of nitrogen to grams, and then kilograms. That'll tell me how much I use. So 5.22 kilograms of hydrogen, turning it into grams. A mole of hydrogen weighs that much. 3 moles of hydrogen react with 1 mole of nitrogen. A mole of nitrogen weighs 28.02, and then every 1,000 grams is 1 kilogram. And so when I get my answer, it's 24.1 kilograms of N2 that gets used. Okay, cool. Now I know how much of this stuff I used. I was given 31.5. I used 25.1. So the difference between those two numbers is 7.4 kilograms remaining. This is a common question. Your book asks some questions like this. I can promise you there will be a question on the test that is just like this, a limiting reagent problem that asks you to figure out how much of the excess reagent remains. So you want to study this. It's straightforward for the first part, just trying to figure out how much you make, what your theoretical yield is, what runs out first. Students get tripped up here at this second part. And that's because we need to realize that we're asking a new question. What mass of N2 is it? And that's what we need to figure out. Okay. So before I move on to the last one, so there were like 2 examples wrapped up in this one. Are there any questions on what you guys have seen? This one you may need to spend a minute or 2 with. Not right now, on your own when you're studying. Okay. So the last question that we're going to come up with here is iron oxide and carbon monoxide going to make iron and carbon dioxide. Now, what you're seeing here is that this reaction has this reaction here has coefficients in it, so you can be reasonably sure that it's balanced. Which means you don't have to worry about balance. 167 grams of iron oxide reacts with 85.8 grams of carbon monoxide, and that produces 72.3 grams of iron. What is the percent yield of the reaction? Okay. This is a situation where if I have the ability to get moles of more than one reactant, it's a limiting reagent problem. And that is the case here. I can get moles of this first species. I can get moles of this second species. That means that I don't know which one limits my reaction. So I need to do both. So my plan is this. I'm going to go from grams of iron oxide to moles, moles of iron oxide to moles of iron, grams of iron. Laid out, it looks like that. I needed the periodic table to figure out the molar mass of Fe2O3. Something that's relatively easy to look up. In my balanced chemical equation, 2 moles of iron come from 1 mole of iron oxide. And every mole of iron oxide weighs, every mole of iron, I should say, weighs this much. So when I go through and figure that out, it's 116.8. So if all of my iron oxide reacted, I would make 116.8 grams of iron. Cool. What if all my CO reacts? So grams of CO to moles of CO, moles of iron to grams of iron. So all I'm doing is changing this front little bit here. 72 point, oh no. I may have written down the wrong. Worst, I'm just looking at it right now. 1 second. I want to get my calculator not right in front of me. 1 second. So let's see here. 85.8 divided by 31.996 times 2 divided by 3 times 55.85. 99.84. This number here, let me annotate this, live. This number right here should be 99.84 grams of food. And the reason for that is because this number here should be 85.8 grams. Yeah. The mistake that I made that was originally put up here, 85.8 grams. Apologize, guys. The mistake that I made, and I'll just leave it above here, is a transcription mistake. I should have grabbed that number there, and I grabbed this number here. Sorry about that. Okay. So this is the number that I should end up getting with my results. So when I move on, actual over theoretical. So the actual yield that I get was given to me in this problem. I made 72.3 grams of iron. So what's my percent yield? A percent yield is the actual amount that you made. You're usually given that in the problem. Divided by the amount you should have made, your theoretical yield. That should be this number here, this 99.84. I'm going to make that change here. Times 100. So to annotate this, again, doing it live, ever so much fun. So 99.84. So 72.3 divided by 99.84 times 100 would actually give me 72.4%. And I will make that change here. I'll also change this one in the PowerPoint a little later on today when I get the opportunity to do that. So 99.84 is what should be my denominator, which is my theoretical yield. And 72.4 would be the ratio of those two. So it's a little bit lower. And the main error that I made here again is I just grabbed the wrong number from the problem. A very easy thing to do. Okay, so I'll correct this and send out a revised version into PowerPoint. So I'll take the old one down, put the corrected one up. Okay. That, I believe, is my last of the slides. Yeah. So, screen sharing is stopped. Yes, it is. Okay. What questions, if any, do you guys have on the material that we just covered? If anything. Okay. In terms of content, it's very standard content. It's a skill that we're going to come back to again and again for the next, let's say, 3 to 4 weeks in a class like this. Because stoichiometry, or the ability to determine one thing from another, never leaves us in a class like this. Danny asked the question, what is the difference between actual yield and limiting? So an actual yield is, with all the ingredients I have, I should have made 10 cookies, but I actually made 8 because I was putting too much in the pan each time. So that's your actual yield. Usually that's a number that's given to you, or if you're in lab, that's like the mass of your product at the end. That's your actual yield. A limiting reagent is whatever reagent limits the amount of stuff that you can make. So whatever reagent runs out is your limiting reagent. Your limiting reagent would not be the same as your actual yield. Those are two entirely different things. Hope that helps. Okay, so as a reminder, and I'll send this out via email, I'll get you guys some times for what you can expect on the test. But there will not be a class on Thursday. You guys will have that time to use for your test. It'll be open from 12:01 to 11:59 on Thursday. You'll have all day to complete it, but once you start those time sections, okay. If you have any questions, I will be around. I know I'm going to hang out for one person, and that should be pretty much it. So I'm going to, the problem we just did, the 98.4, be the theoretical yield and the limiting reagent. It is not. The problem we just did, the 98.4, was the theoretical yield, and the limiting reagent is what produced that. So the limiting reagent, I think in that case, was CO, carbon monoxide. Yeah. So when we're done, 98.4 is grams of iron. Okay, so limiting reagent, that's one of the reagents, and grams of product, those are two entirely different things. It just so happens that whatever is your limiting reagent will tell you what your theoretical yield is. So it's, I think what you're getting at is close enough, but you want to make sure like you understand the difference between those two. Okay, I will stop the recording and